Hi, I'm Darren and welcome to Level Up EE Lab. I'm still working on my MicroTAC cell phone project, and today's little episode will be about converting the digital audio back to analog. Let's have a look. Now that I've got the front end of the audio conversion working, let's tackle the back end, digital to audio. On the block diagram, I'm showing this as starting with a pulse width modulated signal coming out of the Nano that's then fed into a low-pass filter and finally into an amplifier before feeding that into headphones or a speaker. But before I committed to using that approach, I first wanted to explore the possibility of converting the digital stream directly to an analog signal. Unfortunately, the Nano, or more precisely the Atmega 328P, does not have an integral D to A converter. I'd have to add an external chip to get that ability. So I looked at a couple of options, starting with the MCP4725, which is a 12-bit D to A that runs off an I2C interface. I also looked at the MCP4901, which is an 8-bit D to A that runs off the SPI interface. Both of these chips have specs that seem to be quite compatible with generating the audio frequencies that I need. And both of those interfaces are pretty easy to implement in software, but I found out pretty quickly that the execution cycle overhead, especially for the I2C bus, is a lot more than I expected. I was really struggling to get even a basic program to work at any frequency above about 8 kHz, which gave me concerns about having enough bandwidth. I was also seeing a lot of jitter on the output. You can see it here on the scope. That made me really nervous because if I truly were topped out at about 8 kHz, then this jitter was certainly a concern for the quality of the conversion. Maybe I could solve this issue, but after burning more hours than I care to admit, I shelved this idea for now and instead went back to the PWM to audio approach. Getting custom PWM output from the 328 requires manipulating a hardware timer, and the 328 has 3 of them, each with a ton of configuration options. In fact, there are so many parameters that it's very intimidating as a newbie to understand where to start. Fortunately, I ran across Kevin's blog post on Arduino PWM sound output, and his explanations really clicked with me. So I set up his example code, and right away I got the Nano to output a 32 kHz square wave using timer number 1 that was pulse width modulated to replicate a 440 Hz sine wave. Nice! So the next step in software is to take the digital signal input from pin A0 and push it out as a PWM output on pin 9. But before I can do that, there's one final chunk of hardware that I need to insert into this chain. It's another low-pass filter and an audio output amplifier. The filter is necessary to remove the PWM carrier frequency and smooth out the remaining signal. The amplifier isn't strictly necessary. You probably could connect earbuds after the filter and likely get some audio response, provided they weren't low impedance earbuds. However, it's always a best practice to provide isolation between low-level signals in the outside world, and here I think another LMV358 will do the job. Note that I'm using it as a buffer, no amplification. That's because on the input side I have plenty of voltage, and all that I need to do is provide some impedance transformation. And for earbuds or headphones with at least 50 ohms impedance, the 358 should be able to supply enough current. If I wanted to connect an 8 ohm speaker, however, I'd need a different amplifier. Another good reason for using the 358 is I've already got a spare one here on my breadboard. The SOIC8 package has 2 of them in there. Let's look now at the low-pass filter. I decided to get a bit more aggressive with the roll-off here, so this filter has 2 stages. However, I have chosen a pretty high cutoff frequency of around 6 kHz for starters. Notice that the second stage, the one made from R11 and C7, has 10 times the resistance and 1/10 the capacitance as the first stage R10 and C6. That's commonly done to maintain the same cutoff frequency, but now the second stage has 10 times the impedance as the first stage, so that the second stage doesn't appreciably load down the first stage. Coming out of the filter, I'm using R12 and R13 as a voltage divider. I could still have 5-volt peaks coming out of the filter, and that's too much for the op-amp input. So this resistor combo knocks it down by 80%. C8 is a DC blocking capacitor, and R5 and R6 provide DC bias for the amplifier non-inverting input. R14 provides some medium impedance load on the op amp when there's nothing attached to the output, and finally C9 provides DC blocking for the output, and R15 sets the output impedance. 50 ohms is compatible with the earbuds and headphones that I plan to use. As usual, I did a simulation before building the hardware, and here's what it looks like. A quirky twist here is how to simulate the modulated PWM signal. I got lucky and ran across a post on Stack Exchange for how to drive a Schmitt trigger with a sine wave input at the audio frequencies and a square wave input at the carrier frequency. The resulting output is exactly what I needed. When the audio frequency sine wave is at a maximum, the duty cycle of the PWM wave is near 100%. And likewise, when the sine is at a minimum, the PWM duty cycle is near 0%. I've reconfigured the simulation to examine two different audio frequencies, 100 Hz and 3 kHz. Let's run it for 50 milliseconds and examine the output. As expected, both signals take some time to equalize around 0 volts. Now, I could get that to settle faster by reducing C9, but most importantly for now, look at how a sine wave has been restored. It's not very clean though. There are still some higher frequency components there when I zoom in, but it's certainly looking good enough to proceed with building up the circuit. Before we get into the lab, let's take a quick look at the software, and this is all that I need to do a demo here. It's really simple, fits on one screen, and from a high level, I've got one volatile variable here, an unsigned 8-bit integer called PWM val. That's what I'm using inside of the interrupt timer every time it gets fired to write to this variable OCR1A, which I won't get into the gory details here, but that's one of the parameters that you set when you set up your timer. Now the rest of those parameters I've set up here in the setup for about a 32 kilohertz, I think it is, fundamental carrier frequency. OCR1A is set for the duty cycle. So by taking that value and adjusting it, I can set the duty cycle of the PWM waveform. Now, in order to set that value to what the input is coming from pin A0, the analog pin, that's within the main loop. I do a quick read of that pin, and then I have to do a little bit of math here to scale that correctly so that I get 0% to 100% PWM modulation based upon what the analog reading is when it gets digitized. And that's really all there is to it. I think the timer is running much faster for the interrupt than the loop runs through, and that's fine. That would just mean it's writing the same value more than once to the PWM output. But I think at this point it should work, and let's get to the lab and check it out. Okay, I've got the circuit all built up on the breadboard, and I'll do a quick zoom in here to take a close look at it. Really not that much to it, and it worked right out of the gate. And I've got it set up right now, so the Simpson's providing the input signal, the variable frequency sine wave, and on the scope, of course, in the background, the yellow trace at the top, that's the input, and ta-da, that purple one is the output. And I'll zoom in on the scope here in a moment so I can take a closer look at it. Especially as I vary the frequency of the AC wave input. Now I am able to hear it just fine on these headphones, but the difficulty I had was getting the audio in such a way that you guys can hear it. And what I came up with, I don't have it hooked up right now, but my microphone preamp, I was able to plug this into the output of the breadboard circuit and then take the output, where is the jack? I guess that's right here, the output of the microphone preamp, and put that into my laptop and do audio capture on it. And so we'll take a listen to 3 different samples here. One is going to be with the Simpson with the variable frequency AC. The second one I'm going to do is play a music track. And then the third one is going to be an audio track that I had recorded in a prior episode just so we can listen to what a better quality original sound looks like versus what's actually coming out of the circuit. And you'll be able to judge for yourself what the quality is. So let's have a listen. Okay, I've changed my setup here a little bit. I'm now driving the input with my iPod Classic, and I'm playing the theme song from Level Up Double E Lab to keep myself out of any copyright problems. So let's give a listen to it. As a final demo, I've taken one of the voiceover tracks from my prior episode and played it to the input. The final element that I need in this section is a low-pass filter. The bandwidth of the Max 9814 is 20 kHz, which is much more than I need. For basic voice communication, around 3 to 4 kHz is plenty. But the bigger issue is the sampling rate of the ADC. Now, I haven't settled on one yet, but I know it's not going to be anywhere near 40 kHz, which is the absolute minimum needed to avoid aliasing issues. I'm really tempted at this point in this project to continue tinkering with those circuits in the software to optimize the sound quality. For sure, those were just first pass attempts to prove that it would even work. But like I said in the beginning of the series, when you work on a project of this scope, it's really tempting to get your attention diverted to work on the easiest elements or those elements that you find the most interesting. But what I need to do is stay focused on the next hardest challenge. In this case, what I need to focus on next is inserting that RF block into this audio chain and proving I can maintain at least the same level of audio quality with that additional overhead. If I cannot, then any optimizations that I might have made to the hardware or the software could just end up being a waste of time. So that's going to be the topic for the next episode in this series, inserting these little NRF modules into that chain and seeing if the Nano is still up to the task. If it's not, then I'll be searching for a more powerful microcontroller, perhaps something in the Teensy family like one of you viewers suggested in the comments on the prior episode. I do hope you're enjoying this series as it progresses, and as always, I thank you for watching my channel. So until next time, bye for now.